We're on our second multiple choice topic, which is over differentiation. We have had a lot of techniques for taking a derivative of a function. Most of them we covered very early on in the semester. First of all, you need to know the definition of the derivative, the definition of a derivative. So be able to recognize that and know that it represents the derivative. We also had the alternative definition of derivative, which was for finding a derivative at a single value of x. So you need to recognize that as being the derivative of a function at some value of x. We have the power rule for derivatives, which we have used extensively. We know the product rule for finding the derivative of a product of two functions, and the quotient rule for finding the derivative of a quotient of two functions. And we have the chain rule, which is the derivative of a composition of functions. So know that when you're applying the chain rule, you take the derivative of the outer function, keeping the inner function the same, and then you multiply by the derivative of that inner function. Know special cases, derivatives of all the trig functions. Know the derivatives of inverse trig functions, derivatives of log functions, and the derivatives of exponential functions. It's impossible for me to give a type of everything that you might see finding the derivative, but I do have some examples here. So let's take a look at these examples. First of all, this is a common type of question asked on the AP exam. The derivative of a power of a trig function. So remember that we think of this as tangent of 4x all to the third power. That's exactly what it means. So then we're just applying the chain rule here. So the power times the leading coefficient, and then we keep the middle the same. In the chain rule, you keep that the same, decrease the power by 1, and now we need the derivative of the inside. Well, the derivative of tangent is secant squared. So we need to multiply this by secant squared of 4x. Now we multiply by the derivative of its inside, which is 4. So this derivative would be 12 tangent squared of 4x, secant squared of 4x. That would be that derivative. Number 2, derivative of an inverse trig function. This is arctan. So remember our little formula for the derivative of arctan would be u prime over u squared plus 1, or 1 plus u squared. With that addition in the bottom, doesn't matter which comes first. So f prime here will be the derivative of our argument. We're just using the chain rule there. All that is a little chain rule. This u prime comes from the chain rule. So 10x over u squared plus 1. Number 3, the derivative of arc sine. So for arc sine, the formula for that is we're going to use the chain rule, so we'll have a u prime up on top. On the bottom we have a square root 1 minus for arc sine u squared. So know that form for the derivative of arc sine. The derivative of our argument is 12x squared, and again, that just came from the chain rule. In the denominator, we have square root 1 minus the square of our argument, so 16x to the 6th. Derivative of arc secant. Well, for the derivative of arc secant, we're still going to have u prime up on top, chain rule. On the bottom, we have the absolute value of u, square root u squared minus 1. If you want to see the derivation of these, go back to Unit 8 was where we did that. You can go back and look at the notes for that. So dy dx here will be the derivative of the argument from the chain rule, absolute value of the argument, square root u squared minus 1. Now, we can simplify this, and I'm not simplifying a lot of these. Well, I won't be simplifying a lot of these, but these will be multiple choice questions on the AP exam, so you will need to simplify. So for this one, this 3, remember this is the absolute value of 3 times the absolute value of x squared, right? Well, if you square x and then take the absolute value, it will always just be x squared, correct? So we're going to have here 6x divided by 3x, which is just 2. So simplified, this would be 2 divided by the square root of 9x to the 4th minus 1. That would be the multiple choice answer. Number 5, the derivative of a natural log. Well, the derivative of a natural log is u prime over u. The u prime comes from the chain rule, and it's 1 over u, the derivative is. So here, f prime of x would be the derivative of u, so 28x to the 6th, little power rule, over u. This reduces to 7 over x. The other way to do that would be to, before we take the derivative, simplify this. Not simplify, expand this log. This would be natural log of 4 plus natural log of x to the 7th. We can pull that 7 to the front. The derivative then is 0 plus 7 over x. Either way, of course, you get the 7 over x. I usually expand if it's unpleasant to take that derivative, like it is over here. This would be unpleasant to take this derivative of. For number 6, we really don't want to take u prime here if we don't have to, right? This would be u prime over u. So we would have a product rule, a quotient rule, we'd have a lot going on. So definitely expand this log before we begin. So this would be natural log of that 7x. We could expand that a little bit, but I can take the derivative of 7x very easily. Plus the natural log of this square root. Well, I am going to move that 1/2 power on the square root to the front from the square root. So, and then minus natural log of sine x. Now it's going to be very easy to take this derivative. So h prime here would be, this would be 7 over 7x, so 1 over x again. And this would be 1/2. U prime is just 1 over u. And the derivative of sine is cosine over the sine, over the u. And simplified a hair, this would just be, they would probably change that to cotangent. That's it. Okay, let's take a look at the next one. So find the slope of the line tangent to the curve. That's just the derivative. And we have here y is equal to 3 to the 7x. So what's the derivative of that? So y prime here would be. So here's what I'm thinking to myself. It's like an e to the 7x, but it's not an e, it's a 3. So I need to begin by multiplying by natural log of 3. That's my thought process. And then we just have the derivative, we take u prime, so that would be the 7, and then we have 3 to the 7x, just like if it was an e to the u. Then we put in 1 for x, so we'll have natural log of 3 times 7 times 3 to the 7. Number 8. Here we need to apply the power rule. So the derivative of x squared is 2x. Leave the e to the negative 5x alone. Now we're going to leave the x squared alone and multiply by the derivative of e to the negative 5x, which is negative 5 e to the negative 5x, u prime e to the u. To clean this up, they might take out an x, and they might take out that e to the 5x. We'd be left with a 2 minus 5x, and that is a simpler looking form than what this is, so they would probably do that in a multiple choice question. And number 9, we need to apply the quotient rule. So for the quotient rule, I start at the top and take the derivative. Well, I have that 2x, so the derivative of that is going to be 2, and now I just have like cosecant of u. So the derivative of cosecant of u is negative cosecant cotangent, leaving u each time. Multiply by the denominator, and then minus the derivative of the denominator, and now we leave the cosecant, the numerator, the same. All divided by the denominator squared. Quotient rule. Okay, number 10, we have a log to a different base. So this is like ln, but it's not ln. That's my thought process. So I begin by making it behave like ln by dividing by ln of 2. Remember, for the exponential, we multiply by ln of that base. For a log, we divide by ln of that base. And now it behaves just like a natural log, which is u prime over u. So this would be 1 over 7x ln of 2. Maybe they would write it like that. Number 11. To find dy dx, find the slope of an equation given to you like this. So it's going to be unpleasant to solve this for y. So I'm not going to solve it for y. I'm going to use implicit differentiation, which means we are going to take the derivative of both sides with respect to x. So we're taking the derivative with respect to x. So the derivative of 3y squared is 6y dy dx, little chain rule. That's chain rule there. Plus 7 dy dx. First you take the derivative with respect to y, and then you multiply by dy dx each time. The derivative of negative x is just a negative 1. The derivative of 14 is 0. The derivative of negative 2xy, we're going to need to use the product rule. Product rule here. So the derivative of negative 2x is negative 2. Leave y alone. The derivative of y here, I'm leaving the negative 2x alone, and the derivative of y is dy dx. Now we need to group all of our dy dx's together and get everything else to the other side. So I'm going to leave these two terms here. I'm moving this term to the left where it will be positive. And while I'm doing that, I'm going to take out a dy dx. So I'll have dy dx times 6y plus 7 plus that 2x is equal to, and I'm just moving this 1 to the other side, so it'll be a positive 1 minus 2y. And then we simply divide by whatever's with our dy dx. Little implicit differentiation. Chain rule. Okay. What will we do with this? Well, I recognize that there are two ways to do this. First of all, I recognize that this is my definition of the derivative. Let me plug in. This is the definition of derivative. So one way to do this would be to say, oh, this is the definition of the derivative of sine of x. So this is the derivative of sine of x, which is cosine x. So the answer is B. Now, I know that some kids don't like to do that. So what's another way you could do that? Because this confuses kids sometimes. Another way you could do that is treat this just like any other limit. H is going to 0, so we have sine x minus sine x, which is 0, over 0, so we can use L'Hopital's rule. Well, through L'Hopital's rule, we would take the derivative of the top and the derivative of the bottom. Now, this is important. What do we take the derivative with respect to? We are so used to taking the derivative with respect to x. However, h is what is going to 0. So we take the derivative not with respect to x, but with respect to h. So the derivative of sine of x plus h is cosine of x plus h times the derivative of h, which is just 1, minus the derivative of sine x with respect to h. With respect to h. This is just like a constant. So it's just 0. All divided by 1. Okay? So you're taking it with respect to h. So the derivative of anything with just plain old x's in it, x here is not a function of h, so it's just 0. The derivative is just 0. Now you let h go to 0, and you get cosine of x. You're done. So that's an alternative way. I kind of prefer to think of it like this, but both ways work. Okay? Here's another one. This is the alternative definition of a derivative. So in my mind, this is the derivative with respect to x of natural log of x evaluated when x is 3. So this would be 1 over x evaluated when x is 3, which is 1 over 3. So to me the answer is quick, easy A. However, we could use L'Hopital's here, because again you get 0 over 0 when you just plug in 3 for x. This would be the limit as x goes to 3 of, now this time we are taking the derivative with respect to x because x is what's going to the limit here. So the derivative of ln x is 1 over x. The derivative of ln 3 is 0. The derivative of our bottom is 1. So now let x go to 3. That one was a little bit easier. So maybe when you have x's, go ahead and use L'Hopital's. When you have these h's, recognize that's the derivative. So it's the definition of derivative, so go ahead and take the derivative. My 2 cents worth. Okay, number 14. For values of h very close to 0, which of the following functions best approximates this? Well, when they say this, I got this wording from a question on AP. For values of h very close to 0, that is the limit as h goes to 0 of this. So this would be the definition of the derivative of secant of x. That's the definition for that. So the derivative of secant x is secant x tangent x. D. So a very, very brief review of derivatives. But like I said, there are tons of derivatives. It would be impossible for me to give you an example of every type. So go practice, do that worksheet.